Everybody picked a number?
Yeah.
All right. Somebody tell me what their number is. Somebody give me a number.
4.
I heard 4 and 2 and one more number. 18? Okay. So everybody agree it could have been any three. I didn't plant them because you guys are like, whatever, man. You could have talked to them and promised them. Oh, shit. If you think that I'm capable of that, then none of this matters. It could have been anything. So, everybody got a calculator, right? Okay, you guys take a minute. This is my boomstick. No, this is my population. Put this into the list and tell me what the mean and standard deviation is. How do you do that in the calculator? You have to use what? Put into a list and use 1 var stats. There it is. Sorry. This is a good review because we're going to be doing this kind of thing for a lot of problems very soon. You got to know how to use this thing. Oh, hit stat, and then number 5 is setup editor. See that? Do that, and now and hit enter. All right, now set it up for you. Now go back in. All right, what do you guys get? Yeah, 8. And notice the calculator says X bar, but it's just a calculator. We're the humans. We know it's a population, so I know it's mu. And it gives me 2 standard deviations, but which one do I have to use? The population one. So that's what? We know it's got to go at least 3 places, right, for crazy ass Mr. Waller. Okay. Yeah, refer to yourself, Jeff. You are right now, Jeff. All right, so, these are the information for individual data points. This number represents the average distance that every data point gets away from the mean. Looking at this, does that make sense? 18 is 10 away, 2 is 6 away, 4 is 4 away. So on average, about 7 away. That makes some sense. You guys with me? That's that. We know that's what standard deviation means, hopefully by now, because I asked you that question on the first test. It's the average distance from all the data points to the mean. I like it. But that's for each individual data point. And that's the mean of each individual data point. Now, I'm going to take a sample of size 2. I'm going to take not just a sample, but I'm going to take all samples of size 2. All right. So I'm going to these 3 numbers in a hat, and I take one out, and I drop it back in, and then I take another one. So it's a sample of 2. Is everybody with me? You guys with me? Or those of you who want to be with me, are you with me? Some of you guys are doing other things at the moment. Great. So example 1 sample would be 2 and 2, or 2 and 4, or 2 and 18. That's amazing. So the other ones are pretty straightforward, right? Same stuff, but now with just a 4 first. And then the same stuff, but now with an 18 first. Does everybody understand what it just did? That's all the possible picks if I take 2 of those papers out of the hat with those numbers written on there. All right, so I know the spread number, the standard deviation for the individuals. What I want to do now is I'm going to calculate the means of all my samples. Let me put a little X bar here. So for example, what's the mean of 2 and 2? 2. 2 and 4.
33.
That's crazy. Whoever picked all the even numbers, good job. That's nice. 2 and 18? 10. Good. 2 and 18 is 20, divided by 2 is 10. It's crazy. 4 and 2, we did it already. 4 and 4?
4.
Coolness. 4 and 18? 11. Is everybody seeing where those numbers are coming from? Because what's the whole idea of chapter 7 is instead of taking each person or each thing, I take groups of people or things. and use their means. And that's what we are doing right now concretely, not some freaky ass Florida and I got people certain ages. I don't see those people, Jeff. Oh, here, you can see the freaking numbers. You can see what I'm using. And the numbers came from you, so I didn't make whatever's going to happen purposefully. It would happen no matter what the hell the numbers were. All right, here, 18 and 2 again. 18 and 4. 18 and 18. 18. Yeah, because the average of two numbers is always the number in the middle. If the average of three numbers, you never end with that shit, right? For example, the average of those three numbers is 8. Are you guys with me? So if I just have two numbers, the average is sort of a silly thing. It's just the number in the middle. Once I get 3, 4, 5 numbers, it's not that easy. Okay, I like it. But again, how do I get the average? 2 plus 18 is 20, divided by 2 is 10. But 10 is also 8 away, 8 away. It is in the middle. Yeah.
How is the mean of 18 and
18 plus 18 is divided by 2. Yeah. So if I have the same data point repeated, the mean is that. That's kind of beautiful. I like it. Is everybody sort of with me?
Yes.
So remember the Florida thing. My first picture was individuals. This. My second picture was groups of size whatever, in this case size 2. This. So now my data are these numbers. They're all the sample means. Yes? So here's where we're going towards. I can do a problem. Every problem we've done so far is if I pick one person, what's the probability that their test grade is greater than 70, right? Let me say this again. This is a problem. We've been doing this problem for the last 3 classes. Pick one grade. What's the probability their test grade is greater than 70? If they give you the mean and the standard deviation, you have to agree that that's what we've been doing. Yes? Because I love it. You guys are like, I don't know, man. If I give you a mean and a standard deviation, and I tell you it's normal, can't we calculate probabilities everywhere because we got the sheet of answers? All I have to do is turn them into z-scores, right? Stay with me. Do we work with individual things in statistics all the time? No. What do we normally work with? Sample. So I need to figure out a process. Does anything change if the question becomes, what's the probability that 39 students had an average grade greater than 70? Does anything change about the process? Do I still make a z-score? Do I still look it up? Does anything change on the way? So let me ask you this. I think I said this last time. If I went out right now and found one person that was taller than 6'6", just randomly pick somebody and they're taller than 6'6", is that really weird?
Yeah.
It's not really weird. It's a little bit weird. I agree with you. It's like a little, like if you randomly pick somebody and they're 6'6", and you're like, okay. Compare that to, I randomly select 20 people, and their average height is more than 6'6". Is that weirder?
Yeah.
Much weirder. So that's like saying the probability of one person being taller than 6'6" is different than the probability that 39 people, whatever I said, are taller than 6'6". There seems to be a difference, at least in the answer. So there must be a difference somewhere in how we get to the answer to make them different. Okay, maybe. So we're trying to transition from everything you've done so far in chapter 6 is all about one. If you look back, pick one person, pick one dog, pick one pregnant lady, right? That horrible problem about the dude, is he the father? If you haven't done the homework, you don't know what I'm talking about, but oh well. Yeah, these stats problems are always a little bit, you know. They're all about one thing. Bless you. Chapter 7 says, well, that's not what we normally do in statistics. We normally deal with a sample of things. So I'm trying to develop the basic process that we use to see if there's any difference. What is the difference between the two situations when I have individual data points versus samples. So if I knew, obviously this is not normal, but if I knew it was normal, couldn't I then ask all kinds of questions? I put 8 in the middle because it's the mean. Couldn't I then ask you what's probably that somebody got more than 10 or something, right? You make a z-score, look it up. But what tells me how fat or skinny this distribution is this guy. So what we're going to notice now is when I take all the mean, instead of doing all the individuals, which was like this picture from Florida, remember that? And I instead do all the samples of size whatever, in this case we're doing 2, the picture should look more like this. Because what's going to happen more often is a mixture between the two. Picture's starting to look a little weird. All right. My dean's like, what are you doing? All right, so you guys understand the idea. So if the probability question is, what's probably this one dude is taller than something? All right, that's shit we've done. That's chapter 6. I can do it. Let's get the z-score, look it up. If the question is, what's the probability that 70 randomly selected dudes are taller than something on average? Can I do the exact same thing? It feels like the answer to that is no. It should be probably they're taller than 6'6" on average, should be really small probability. Whereas for one dude, it's not that small. It's much more likely that one dude instead of 70 dudes are 6'6" or taller. Holy shit. Okay. So this is individual stuff, and I know the stuff about them. Can you guys now what's my data? Every sample mean. Instead of every individual number, I want every sample mean. So can you put this into list 1 and recalculate these things? Let's see what happens. Remember, these are not numbers I picked. I didn't force this to happen. It's going to happen every time. Yeah. So all your data is 2, 3, 10, 3, 4, 11, 10, 11, 8. There's 9 numbers you're going to put into list 1. That's my new data now, is all the means. So it's just like me listing everybody's age, or me listing every 2 people's average age, 2 people's average age. What do you guys get for the mean? 8. Now please, do you understand, did that change? Did the mean change? It can't. Just because I take 2 of them at a time, did I change what the numbers are? I'm taking 2 of them at a time instead of 1 of them at a time. How could the mean possibly change? They're still the same numbers. That makes sense. So we're like, remember Florida, the mean stayed right in the same place because it was the most likely thing to happen. What's the standard deviation?
5.033. Would it be sample this time?
No, and I'll tell you why. It's a beautiful question. Do I have all of the sample means? Yes. Are there any samples I left out?
So if you wanted a sample mean specifically...
Yeah. Let's not go too far with this. This is still sigma because it is the standard deviation of all the sample means. But that's why this notation looks like this. Because what's this mean? It's the standard deviation for the sample means. It's how the sample means are spread out. What's really funny is, what does the calculator say? It doesn't just say this. What does it have right here? An X. So what's that? And we normally don't write that because we just say we assume that if nothing's there, we assume that this is the standard deviation of the individual values. How spread out every X is. This one is how spread out every X bar is. So I love that the calculator does that. It's sort of like when we put the square root symbol, we know there's a 2 there. We don't write it. So we normally write a sigma. We know there's a little x there. We just don't write it because we know it's there. We have to put the x bar when we're like, oh shit, now we're doing samples. All right. What's it say? Shit and a half. What are you doing? 5 point who to what?
0.
5.033. I like it. All right. So what's happening is there's a theorem called the central limit theorem. The name doesn't matter as much as the substance of it. Every time I write this, I think chicken, lettuce, tomato. But that's central limit theorem. And now I want the chicken sandwich. Central limit theorem says the mean of all the sample means stays the same. That's the whole thing about if I take each person versus 2 people at a time, how can you suddenly become older or younger just because I did that? The average has to stay the same. The second thing it says is that the standard deviation, here's the important thing, does it get smaller or bigger? Remember this whole discussion here? Once I took a sample, these are individuals, this is samples of size 10 or whatever, remember that with the Florida? The standard deviation got smaller because there's a lot more shit right on the mean. So here's the neat thing. How much smaller did, in fact, did that happen? What was the standard deviation before? 7.118. What is it after I take samples? Holy shit. Because now it should be harder for the samples to get further from the mean because I'm averaging, they should get closer to the mean. So, if I would have taken samples of size 3, first off, there would have been a shit ton more of these, right? You guys see what I'm saying? So thank God we're developing a way to do this so I don't have to list all of these. I want a formula that would tell me what the standard deviation would be without actually having to write all the shit down. Sort of like the choose thing. Tell me how long the list would be without me having to make it, please dear God, calculator. It costs enough money. There you are. So what the formula says, it should be the spread for individuals, what I call the original standard deviation, divided by the square root of n. So as n gets bigger, the spread gets smaller. So if I took 3 Grossmont students, is it that weird their average age is 40? Not really crazy weird. If I took 800 Grossmont students, would it be weird for their average age to be 40? Shit, yes, because more of those 800 groups of 800 should be closer to the mean. The standard deviation should get smaller. That's why it's divided by square root of n. As n gets bigger, the result gets smaller. So we just calculated this directly. Why don't I want to do this every time? Because for everyday problems, this list would be stupid big in the millions. I don't want to make that a list. I don't want to. If you want to, don't. Don't do that to yourself. I'm never going to suggest you should. I don't know if you guys, even with this, if I took samples of size 3, it would be 2, 2, 2, 2, 2, 4, 2, 4, 2, 2, 4, 4, and we're not even, holy shit. Do you see what I'm saying? So now imagine if there were 30 numbers, and I'm taking all samples of size 15. Fudge. I want to say. All right. So what does this predict that this, we know what it is. Let's see if it actually comes out the right way. Individual one was 7.118. Divided by the square root of what? How big was each sample? 2. What do you guys get when you do this? See, I haven't even done it. I don't even know. All I got is theory. I know the theory's right, so ha. Shut up, Jeff. Divided by square root of 2. What do you guys get? I'm excited. This is what the theory predicts this was supposed to be. I made a problem where it was small enough that we could do it. What's the theory say this is supposed to be? Anybody got it yet?
I know. It's the same.
I love how you're like, I would hope that some of you guys go, holy shit, you got the same freaking number, didn't you? That little formula got the same answer we got by having to do all this shit. So do I have to do any of this shit anymore? No. I can use that formula to figure out what the standard deviation of groups of size whatever would be. Yes?
How'd you find the 2?
How big was each sample at 2? There you go. So if I would have taken all samples of size 3, n would have been 3.
Oh, okay, so
like
it'll be given to us? Then
Yes, how big the sample I'm taking. Yes, they have to tell me or else I'm screwed.
So would you do this when, like, how do you know when to do it? Like,
Beautiful.
this way?
We're going to do an example problem. I can't remember if I said this or not, but almost always, the derivation of something is kind of gross. And then we say, well, what does all this lead us to? What do we use? This is an insane example of that. Is the idea simple up here? No, it's not. It's okay. It's not simple. It's not simple. But let's do a problem. And I'm sorry, the third thing that says, might be the most important thing in a way, is that if n is greater than 30, the answer is approximately normal, or what I call normal enough. Why is that important? For a probability question, what kind of distribution do I have a chart of answers for? Yeah, dude. So if they took a sample bigger than 30, but they didn't say it was normal, I know the result is normal. I know I can use the z-score chart. All right, you guys look oppressed and depressed. All right, I'm used to that. Let's see. All right, so a really good question. I know it's in your heads is, what the shit does this do to me? All right, here it is. What the shit does this do to me, Jeff? You're never going to have to do a problem like we just did on your own. All of that was just derivation to get us to that. So here's a problem. And then I got a little handout, of course. Let's do one problem together. You know me. Oh yeah, and I got the practice test too. Let me forget that. Given the mean is 80 and the standard deviation is 10.5. We take a sample of 47 things. I love how descriptive I am. Creative and descriptive things. What's the probability that the sample mean is less than 78? All right. So on the surface, do you see how this is fundamentally the same feel of a question that we've been doing in chapter 6? Can you point out the two differences between problems we've done in 6 and a problem from chapter 7? This is related to your question, right? When do I know when to do this shit? That's a great question I'm asking. I know how to do this. When the shit do I do it? Oh shit. There's two main differences. One is, what symbol is normally here? X. And now I've got X bar. Why do I have an X bar? Because I took a sample. So those are the two differences. I took a sample and I'm asking a question about the sample mean. That's my trigger to know to do that shit. Now, what is it about this problem that tells me I can do anything, that I can eventually get the answer? And where's the answer going to come from? I love you guys. What's the last step going to be for this kind of problem? Look on the chart, yes. And I can only use it if I know the distribution is normal. What is it about this problem that tells me I can do any of that? N is
Greater than 30.
47, which is bigger than 30. Good old chicken lettuce tomato says you can do it. I can't make the number 3. That's a problem for my profession. If n was 27, we would be screwed unless the problem said it's normal. I want you to realize, every problem we did in chapter 6, didn't I have to tell you it was normally distributed? Why? Because the sample size was always 1. So I had to tell you it was normal. Now, if the problem doesn't tell me it's normal, what saves my ass? If I got a big enough sample. All right, so here's the beautiful thing about all this shit. The one thing that changes, what changes? What do I change when I'm taking a sample of things? I'm asking about the sample mean, what changes? What becomes a different thing? What has a different value? Does the mean change? No. Standard deviation changes. So what's the new standard deviation? I call this the new standard deviation, but it's the spread for sample means. But you can see why I just call it the new one. It would be the old one divided by square root of n. So that would be 10.5 divided by square root of 47, because I took a sample of 47 things. I'm asking a question about what's the chances that this group of 47 will be here. Well, I've got to know the spread for all groups of 47. What have we done before? I know how spread out the individuals are, and I ask you a question about the probability of individual thing. All right, that's beautiful. Those fit together. Now I've got, here's how individuals are spread. What's the probability of group? Oh shit, I can't use that number. That's for individuals. I have to use the one that's for groups. No other ideas change. The z-score formula stays the same once I change this. What do you guys get for this? 1.532. Yes? Okay. How much new shit have I done on this problem so far? This. And that's the last new thing I've got to do. Now I draw my picture. What goes in the middle? 80. I like it. And I'm interested in 78. And I want to probably less than. It's just when I go to make my z-score, I don't use this. I use this. That's it. So I know on one level you're like, my flipping God, Jim. It took us how long to get through this idea? And on a problem, that's the one thing you've got to do. You got to know when to do this, and then accept that's the only tweak to the whole thing. So how do I make a z-score? I want to make a z-score out of 78, so it'll be x 80 divided by 1.532. I can't use this number because that's how spread out individuals are, and the question is not about an individual, it's about a group. So I need to create the number that represents the spread of all the groups.
For these types of problems, you want 3 decimal places?
Standard deviation is always at least, well, I don't know. Whatever, you'll take points off. Standard deviation always goes to at least 3 places. One person saves your ass. I know you guys all know that, don't you? Please tell me that. Let's see how long. So I told you a long time ago, make everything 4 places, your ass is covered, except for what? Z's, because what's the z-score chart need? 2. So if you forget, the chart tells you, I only want 2 places. Okay, love you guys. Let's finish this out. You alright? So what do you guys get for this? So you get -2 over 1.532. Yeah, sounds about right. -1.31. And then you just looked it up and you're done. How much extra work in this problem compared to another problem like it in chapter 6? 1 extra step right there. That's it. So let me give you this. Whatever you get when you look at -1.31, you guys can tell each other. I'm going to give you this little handout. Let's see how far we can make it. And then after I finish passing these out, I'll give out the practice test and you just put that away.
worksheet we're working on right now.
Sleep.